In this question, a scientist has a nitric acid solution of known concentration and an ammonia solution of unknown concentration. The scientist uses the nitric acid as the titrant in the burette and a known volume of the ammonia as the analyte in the conical flask. So to get a better idea of what's going on, in this question, we have ammonia in our conical flask with a known concentration. And then we're adding nitric acid to that ammonia solution. We've been given the molecular form of the chemical equation for this reaction. Let's also write out the ionic equation for this reaction. So HNO3 nitric acid, that is a strong acid. So that is going to split up into its ions, H plus and NO3 minus. NH3 is a weak base. That means that most of the NH3 is staying as an NH3 molecule. Now, when these react together, we're getting ammonium nitrate formed, which is a soluble salt. So we're getting NH4 plus and NO3 minus. So we can see here that NO3 minus, that is a spectator ion in this reaction because it doesn't participate. It's there at the beginning and the end. The H plus and the NH3 form the NH4 plus. So those are our participator ions. Again, the scientist measures the pH of the solution as the titrant is added. So we've got pH on a y-axis and volume of titrant on the x-axis. In this question, we're starting with ammonia in the conical flask, which is a base. So it makes sense that we're starting with a pH greater than 7. Our job now is to go through the graph at each moment and figure out which species has the highest concentration at each point, NH3 or NH4 plus. So let's again draw a diagram representing what's going on in our solution. So to start with, we have ammonia in solution. Since ammonia is a weak acid, most of it stays as those ammonia molecules, NH3. Only a very small amount of it dissociates to form NH4+. So I'm just going to write NH3 in here. I'm not going to show any NH4+ to start with because so little of it dissociates, only a tiny bit. So that's what we're starting with. So that's what the solution will look like with 0 liters added. At points A, B, and C, we have 0.01, 0.02, and 0.03 liters of our titrant added. Then at D, we have 0.06 liters of our titrant added. So D in this question, we can see that's the moment where we have this flexion in our graph. And that is going to be the equivalence point for this reaction. So I'm going to go ahead and fill that in down here. That is the equivalence point. It's at D. That is the moment where the reaction is complete. So for the reaction to complete, all the NH3 that we had to start with must have reacted with the HNO3 we added. So based on our equation here, since we have a 1-to-1 ratio, that means the moles of HNO3 added must be equal to the moles of NH3 in the conical flask. So at A, we've just added a little bit of our titrant, which is the HNO3. So let's go ahead and show that here. Remember, HNO3 nitric acid is a strong acid, so it's going to split up into its ions. We're going to have a H plus and NO3 minus. Now, according to our ionic equation up here, the H plus and the NH3 will react together to give NH4 plus. So for example, this H plus and this NH3 will react together to give NH4 plus. So as we're starting to add our titrant at point A, we're getting some of our NH3 converted into NH4 plus. Now, our goal is to figure out which species has the highest concentration at each point. Do we have more NH3 or more NH4 plus? So to start out, we just have NH3. Then as we add our titrant, we're getting more NH4 plus formed. At some point, we're going to have equal amounts of NH3 and NH4. So the point when that happens is going to be where we have half of our NH3 reacted into NH4 plus. So in this situation, I started out with 6 NH3 shown on my diagram. So if I add 3 HNO3, I've already added 1, so let's add 2 more. An H plus and an NO3 minus, and another H plus and another NO3 minus. Again, that H plus is going to react with the NH3 to form NH4 plus. So I started out with 6 NH3s here. When I've added 3 sets of HNO3, the result is that I have 1, 2, 3 NH3s, and I have 1, 2, 3 NH4 plus. So at this point, when I've added half as much HNO3 as there was NH3 to start with, we're going to have the concentrations of NH3 and NH4 plus being equal. So on my graph, at point D, that's my equivalence point. That's when I have all my NH3 reacted. Half of the volume added is going to get me to that half equivalence point where I have an equal amount of NH3 and NH4 plus. So half of 0.06 is 0.03. So that's going to be this point here. So at point C, I've got equal amounts of NH3 and NH4 plus. Before that, I had more NH3. Some of it had started to react to form NH4 plus, but we still had more NH3. To get to point D, we have to add the rest of the HNO3 so that all of our NH3 is reacted. So I've got 3 NH3s left, so I'm going to add 3 HNO3s. Again, since it's a strong acid, they're going to be split up into H plus and NO3 minus. And again, any H plus is going to react with any NH3. To form NH4 plus. So at this point, at point D, all my NH3 has reacted to form NH4 plus. So you can see in our diagram here, we're showing 1, 2, 3, 4, 5, 6 NH4 plus, and we don't have any NH3 shown here because it's all been reacted. So that is our equivalence point. So that's our point where we have more NH4 plus because all the NH3 has reacted. Let's just fill in about our half equivalence point here. We said that's when our NH3 and NH4 plus have the same concentrations because half of what we originally had has been converted into NH4 plus, and that happens at point C on this diagram. We're also asked down here, what is the pH at the equivalence point? So looking at our diagram here, we said D is our equivalence point, and our pH at that point is actually 4. So we can fill that in here. The pH is less than 7. The reason why is that because we have a weak base reacting with our strong acid, our weak base forms NH4 plus. So at our equivalence point, we have NH4 plus. But because NH4 plus is the conjugate acid of a weak base, it's actually going to in turn react with the water to form NH3 again. So some of these NH4 plus ions are actually going to form back into NH3 and H plus ions. So because we had that weak base, it's forming NH4 plus, which is an acidic ion that can react in water or dissociate in water to form NH3 plus and H plus. So actually, at the equivalence point, we do have some H plus because the NH4 plus is acting as an acid. So why is this pH at the equivalence point? It's because NH4 plus is a weak acid, so it reacts with water to form H plus. We know that because NH3 is a weak base, and the conjugate acid of a weak base is also a weak acid. Finally, let's look at what happens at point E. This is a point where we have 0.1 liters of our titrant added. So we know D was the equivalence point. That was the moment where all of our NH3 had reacted with the HNO3 added. Now we're just going to keep adding HNO3. And remember, HNO3 is a strong acid, so it's going to split up into its ions. So we're adding H plus and we're adding NO3 minus. Now there's no NH3 left for the H plus to react with. So the H plus is just going to remain in solution. So that's why we end up with our pH getting lower and lower. It's because we're adding more H plus that's staying in our solution, making the solution more acidic. So again, here at this point, NH4 plus has the highest concentration because we don't have any NH3 left. It's all been converted to NH4 plus at that point. So there's our titration between an acid and a base, with one of them strong and one of them weak. So with this type of question, first write out your ionic equation so you can have a think about what's actually going on in your reaction and what ions will be present at each time. Then have a think about the equivalence point and the half equivalence point. Remember the equivalence point, that's going to be that moment of flexion in the graph, and that shows when the moles added are equal to the moles we had initially, and that's completely reacted. Then we have our half equivalence point. That's when half of what we had initially there has been reacted, and therefore the concentration of our base in this situation and its conjugate acid will be equal. So that's why we had both NH3 and NH4 plus having the greatest concentration at point C. Remember, the pH at the equivalence point, when we have a weak acid or base, is not going to be 7. If we have a weak base reacting with a strong acid, our pH will be less than 7, because when that weak base reacts, it forms its conjugate acid, and that acid will then go on to produce H plus ions in water. Conversely, if you have a weak acid and a strong base, when that weak acid reacts, it's forming its weak conjugate base, and that will then go on to react with water to form OH minus ions. So if we have a weak acid and a strong base, we're going to end up with a pH greater than 7 at our equivalence point.